We're Team R406, the Rocklet Troglodytes, and this is the Venus Investigation of Surface and Terrain and Atmosphere mission, otherwise known as VISTA. This mission was designed by an elite group of engineers: Hudson Reynolds, Jackson Preisler, Jared Cartwright, Suraj Kadaji, Evan Lorenz, and Kevin Kuida.
The objective VISTA hopes to accomplish is to land a rover on the surface of Venus, where it can perform experiments to help us learn more about Venus's atmosphere and surface. Our major stakeholders are the government and general public, the various teams that we employ to work on sections of the rover and its launch mechanisms, and the space agency that we obtain the launch vehicle and launch site from. The mission will need to have enough fuel for the trajectory and course corrections. The communication system should be able to reach over 260 million kilometers to deliver scientific and telemetry data. The rover should also be mobile and autonomous enough that it can navigate and avoid obstacles to a reasonable degree, as well as resist the intense temperature and pressure on the Venusian surface. The personnel that work on the rover also have to give clear and regular updates to the public about the rover's status and why it's important, in order to secure public interest and funding. To evaluate risks, we research things that most often lead to failure in the spacecraft and things that were especially important for a Venus mission. This included micrometeoroid collisions, attitude control system failures, engine failures, atmospheric disintegration, and communication failures. Using past research, we evaluated the estimated probabilities of these events occurring and the consequences of system failures. We also researched methods to reduce the severity and probability of these risks. The risks before mitigation show 3 risks that are in the red region, showing that there is a very high risk. After mitigation, there are no risks in the red region, and the highest risks exist in the yellow region.
We started our design process by calculating the delta V that is needed. This is the most important parameter for the design because it will dictate the rest of the sizing of the vehicle. To calculate accurate delta V for the mission, we created a Lambert equation solver algorithm to solve the Lambert differential equation. This equation computes a valid trajectory given 2 endpoints and a transit time. From this transit, the delta V is measured using the patch-conic approximation. To increase accuracy, these are then input into a custom Runge-Kutta integration scheme with in-body dynamics for the satellite orbit. The planet positions are initiated with the Keplerian elements of the orbit. These are then converted into Cartesian elements for numerical integration. This integration scheme is validated using the JPL ephemeris data for the planets. This gives us accurate positions of the planets and for the satellite. To find our final trajectory, we run a large number of simulations with different transit times and different launch dates. From this, we selected a launch date and a transit time with the lowest delta V requirements. Knowing the delta V requirements for the vehicle, we could then size an interplanetary transfer vehicle matching these requirements. We selected a Hydrolox-powered lower stage for high efficiency and a hypergolic upper stage for long-term fuel storage capabilities. From here, we selected engines that used these fuels and had appropriate thrust-to-weight ratios. The other most important criteria is the reliability of the engines. Both of the engines we selected are proven engines with high reliability. With all of these criteria in place, we could estimate the payload that we could put on Venus by sizing the whole vehicle and ensuring that the mass stayed within the payload limits of the launch vehicle.
Research into payloads led us towards a land-sliding rover design. These designs use the winds of Venus as the primary propulsion of the rover. We also have multiple atmospheric probes that release during the payload's descent. On board the probe, there are a multitude of sensors used to analyze the atmospheric conditions as it falls to the ground. This design allows for the probe to collect data for a large range of the atmosphere as it descends. In the original mission that we referenced, the payload was around 500 kilograms. With our additions, the payload weighs around 600 kilograms. This gives us a target for our launch vehicle. We chose the Falcon 9 made by SpaceX as our launch vehicle. This is because of the low cost and high success rate shown in past launches, as well as a payload design large enough to fit our design requirements. The Falcon 9 gives us a total payload capacity of 1.1 tons, so the payload has a margin to grow by around 70%. Our delta V optimization gave us a launch date of June 8th, 2026, and a transit time of 185 days. The mission is launched from Cape Canaveral because this location allows us to insert into an orbit matching the inclination needed for the final transfer orbit with very little additional delta V cost. During launch, the first and second stage of the Falcon 9 is used to get the payload into low Earth orbit. After orbital insertion, the RL-10C Hydrolox stage performs a burn to insert the payload into the Venus transfer, and the AJ-10-190 stage performs the final circularization burn around Venus. Once the payload decelerates, it enters the Venusian atmosphere where the heat shield protects the system from overheating and slows the system down. The heat shield then detaches from the main payload, and the first parachute deploys from the aeroshell to slow the payload even further. At the same time, the atmospheric probes are deployed and start collecting data. Once the probes are released, the land rover detaches from the aeroshell and deploys its own parachute. Once the rover reaches the ground, the parachute detaches.
This project taught our team a lot about orbital mechanics. Additionally, an important part of the project was the interplay between different considerations on a space vehicle. Striking a balance between payload safety and the mass was especially important to our design. In the future, we would continue to work on refining our simulations in CAD to generate a more realistic design.